So here we have a straight infinite current carrying wire which is bent, and the current flowing through it is 11 amperes. And then when we get to the curve, it has a radius of A is equal to 25 centimeters. And we're trying to find the magnetic field at this point P, at the center of that semicircle. So the way to start with this problem is that we need to use these two formulas. This formula is for the semicircle exclusively, and this formula is generally for wires. And there's a reason behind why I'm using this formula for the wires and not this formula that we're usually used to using. Basically, this formula is when both of the angles, theta 1 and theta 2, are equivalent to 90. Because when they're both 90, we get sine of 90 plus sine of 90, which gives us 1 plus 1, which gives us 2, and then when we do 2 divided by 4 pi r, we get essentially mu OI over 2 pi r. Now you see how we've bent the wire. We're gonna basically divide this diagram into 3 pieces. Piece number 1 is the wire, but it's no longer infinitesimally long. Piece number 2 is the semicircle that we formed, this entire thing. And piece number 3 is the wire again, but it's no longer infinitely long. Now, what we've done with piece number 1 is that if it had continued all the way to infinity onto the left hand side, we would have gotten an angle of 90 degrees on the left, which would be our theta 2. And then on the right hand side, we'd also have an angle of 90 degrees, which would be theta 1. In our case, we kind of bent this piece and it's no longer infinity, but it's a semicircle. So the angle here that this wire forms now over here is 0. So we're saying that theta 2, we're saying that theta 1 is equal to 90 degrees and theta 2 is equal to 0 degrees. Theta 2 would be here, but it's no longer there because the wire is now no longer infinitesimal, no longer infinitely long. So coming back to that formula I talked to you about, we have mu OI. This is the original formula for the magnetic field of a wire over 4 pi r, and then you have sine theta 1 plus sine theta 2. Now this is segment 1, so I'll call it B1. When we plug in these angles, theta 1 is 90 degrees and theta 2 is 0 degrees. We get sine of 90, which is 1, plus sine of 0, which gives us 0. So essentially we get the following formula: mu OI over 4 pi r times 1 times 1 plus 0, which is just 1. Now I wanted to point something out for the third segment as well. It's the same thing for the third segment, except that when we talk about sine of theta 1 and sine of theta 2, the specific portion of that larger formula, we see that if the wire here was infinitesimally long, the angle here would be 90 degrees. Theta 2. And the angle here is already 90 degrees regardless. Theta 1. So theta 1 for this segment of wire here is still 90 degrees. But theta 2, this guy here, is 0 degrees. As I explained earlier. Because we've bent the wire into an arc. So we'll use a different formula for this arc instead of the usual formula of the wire. So essentially the basic idea with this problem is just that you break this entire thing into 3 pieces, this entire diagram into 3 pieces, and you find the individual magnetic fields using these 2 equations here. So essentially what I'm trying to say is that the formula for the other segment down here of the wire is going to be the same as the formula for this segment up here. Now I'll erase all of that. Oops. Now I'll pay attention to this arc over here. Forget that, I'll have to just sketch it. I was trying to make it more straight, but it's fine. So basically we realized that what we have here is a semicircle, half of a circle. In other words, an entire circle on its own will make an angle of 360 degrees. Half a circle will make a maximum angle of 180 degrees. That's the maximum angle you can reach within a semicircle. And the maximum angle you can reach within a circle is 360 degrees, no more than that. Keep these 2 things in mind. I'll bring in the other formula for basically the semicircle. There we go. I'll just straight up copy paste it. There we go. Now I'll plug in the values first. So mu O is 4 pi times 10 to the negative 7 Tesla meters per ampere times the current. The current is the same through all of these segments, which is 11 amperes. Like I mentioned before, it's 11 amperes divided by 2 times R. Our radius for this semicircle is A, and A was 25 centimeters, which I'll convert to meters, which gives us 0.25 meters. Now to deal with the second part of this equation, this angle in degrees that our semicircle, like this angle here that I've just circled, is the total angle a semicircle can form, which is the maximum angle a semicircle can form, which is 180 degrees. That's 180 degrees over 360. 360 degrees is the angle a circle can form, the maximum angle a circle can form. So it's always the angle of a semicircle or a quarter of a circle, or I don't know, a small piece of a circle. The maximum angle a small piece of a circle or a smaller piece of a circle can form, divided by the maximum angle a circle can form, which is 360. So it's kind of like dividing a piece of a circle over an entire circle. That's what this part of the formula means. We need this part of the formula so that we can sort of accommodate so that we can find the magnetic field by this entire from this entire semicircle, by this entire semicircle. So now I'll plug this into the calculator. And I get a magnetic field from the arc being equivalent to 1.38 times 10 to the power minus 5 Tesla. That's at least the magnitude. That at least gives me the magnitude. Again, the first thing you do with these problems is you always find the magnitude. For now, I'll put the magnitude symbol for both of these. Now I'm going to find the magnetic field of both of these wires. So, well, yeah, 4 pi times 10 to the negative 7 Tesla meters per ampere. This is just a constant. The current was, as usual, 11 amperes. Let me divide that by 4 pi r. What's the radius? The radius, or the distance from this segment to point P, is given by, let's see, I'll draw a triangle here from point P. So actually forget that. We're still using, for the radius of any of these two segments, it's going to be the same. It's going to be equal to A. For some reason, I'm not able to explain it to you, so you'll probably have to ask your teacher. But we're still using A for both of these segments as the radius as well. I mean, one way I can explain it now that it came into my mind is that this is basically the same wire, so we can use that as the radius. I mean, imagine a bunch of point P's. Imagine that all of these are point P's. Then the radius is always going to be A here, A here, A here, A here. Maybe that, I hope, would explain it to you. Otherwise, just ask your teacher. The radius is A as well, so it's 0.25 meters. And now again, I'll plug this into the calculator. That gives me a value of 4.4 times 10 to the negative 6 Tesla. Nice. Now that's one thing we always do with these kinds of problems, is we find the magnitude of the magnetic field first. That's how my teacher taught me. And now I'll sort of get to explaining how do we know the direction so that we can actually find the direction of the net magnetic field at point P. I know the Weber question's already given us the hint that it's going to be out of the page, but let's show how we actually get there. Let's explain how we actually get there. So again, we're going to have to use the right-hand rule on each of these segments separately. Essentially, you want imagine that you have a tablet with you and you have this video open on your tablet, and your tablet is on a table in front of you, right? assuming that you're looking straight down into the tablet and straight down through the tablet, through the table, into the ground. You're going to have your y-axis in this case pointing like this, your x-axis pointed that way, and your z-axis, positive z-axis, is pointing outside straight into the roof or into the sky. Now your thumb is going to point on towards the negative x direction, basically following the current. It's going to point towards the current. And then you're going to roll your arms, or not roll, sorry, you're going to curve your arms sort of like into your tablet initially, until you keep curling your, not your arms, sorry, your fingers, you curl them into your tablet or into the table, and you keep curling them until you form a fist. So initially your fingers are going into the table, then they're coming out of the table as they roll up and tighten into a fist. So you already know that if I look above the wire here, if I look at this in 3 dimensions, above the wire here, the magnetic field is actually pointing into the table or into your tablet. So like basically, let's say your hand is flat on top of your tablet, and initially when your fingers starts, when they start to curve into your tablet or into the table, initially they're pointing into the table, right? So that means the magnetic field is pointing into above the wire here. The magnetic field is pointing into the page or into the table. If you look below the wire, that's when your fingers keep curling and they come back up through the table, or they point towards the sky. So when you're below the wire, the magnetic field is pointing towards you. Now the same applies for the segment down here. I think I can let you do that yourself, but I'll put the answer anyways, so give me a second. That's what it is. Above the wire, above this segment, the magnetic field is pointing towards you. And below the segment, your magnetic field is going into the page. And then the same thing for this piece of the wire, so I'll do that for you as well. You can try testing it yourself. So as you can see, you'll see a trend. If you look at the upper part of the wire, like out here, the magnetic field is always pointing into the page. That's a pattern you're going to observe, because the current is going in the same direction throughout the wire. It's the same wire. And the magnetic field is pointing into the page here and here. So basically, any point inside of this massive curled wire, any point inside of this massive curled wire is always going to have a magnetic field that's pointing out towards you or towards the sky in the positive K direction. So what does that tell us about all of these magnetic fields that we have found? The magnetic field by segment 1, the magnetic field by segment 2, and the magnetic field by segment 3. It tells us that they're all pointed in the positive K-hat direction. Now I'm going to erase all this because it's way too messy. So now that we know that's the case, I'll remove these absolute value symbols. Some teachers really like deduct marks on these things, so just be a bit careful. And we know that now the magnetic field is pointing in the positive K-hat direction for all of these guys. And that's awesome. So now we just add them up. And that's the last point. So the net magnetic field is going to be equal to the magnetic field from wire 1, the segment 1, magnetic field of the other segment of the wire, which is B3, and then the magnetic field by the arc. So what are we doing? We're adding 4.4 times 10 to the negative 6 Tesla K hat to another 4.4 times 10 to the negative 6 Tesla K hat to a arc length, sorry, not an arc length, the magnetic field from the arc, which is this guy, Tesla K hat. Now I'm going to erase that, so just take note of this or pause the video and I'll add this up. Let's see if we get the right answer. I hope we should. And yeah, we do. So the answer is, for the net magnetic field at point P, it is 2.26 times 10 to the power negative 5 Tesla in the positive K hat direction. And we're basically done here. So the main idea behind this problem is just breaking this entire massive curve into 3 segments and then calculating the magnetic field using these 2 formulas essentially. And yeah, now that's pretty much it. Have a good day and take care.